I'll be like, but I'll be all we can do the next.
Okay, so maybe let's start. So today we're happy to have Lars. So Lars got his PhD in 2019 from Amsterdam University. Then he did postdocs in University of Wisconsin Madison, Arizona State University, and this year he moved for a postdoc to University of Minnesota Duluth, where he soon may be transitioning into a tenure track position. So and today he's gonna tell us about black holes in the heat of space.
All right, yeah, thank you so much, and thanks for having me in the hospitality. So I'm sort of quasi-local since I live in Duluth, but this is the first time that I'm visiting here the Institute, so it's really nice to see everybody here and to present some recent work that I did. But before we start, let's just mention some acknowledgements. So what I'm going to talk about today is mostly based on this paper that came out last month that I did in collaboration with these fantastic collaborators, which sort of span different universities and continents. And let me especially highlight the contribution of Pushin Lin, who's a graduate student at UW-Madison, who did an excellent job on this paper. And he will be on the job market, I think, in a few years' time. So keep an eye out for that. But then let me tell you a little bit about the motivation for this type of work, and maybe also more generally the type of research that I do. So I'm a theoretical physicist, and I specifically work on quantum gravity. So if you talk perhaps to the general public, maybe they've heard a little bit about quantum gravity, then they might ask you a question. Well, that's all nice that you're working on quantum gravity, but I thought physics was an empirical science. Where's the observational evidence for quantum gravity? And then perhaps you might need to disappoint them a little bit. One of the best candidates of the theory of quantum gravity that we have is string theory, but we don't have any direct observational evidence for string theory. Yes?
What would you call it then?
I would say, a good question, I would say something that we predict, we measure, let's say that we measure, I don't know, alpha prime corrections or something. That would be a direct, I'm trying to be a little bit provocative here, of course, but we'll see where this is going.
Scattering points.
Yeah.
So indeed, so we'll come to that point precisely. So then you might say that, okay, perhaps you think that also, if I'm thinking about string theory, perhaps also supersymmetry should be in the game. And depending sort of on the precise details of what you're doing, you might expect that there should be low-scale supersymmetry. As you know, at the LHC, we haven't seen any direct evidence for low-scale supersymmetry. Also, we don't have any, I would say, good reason to believe that that is really around the corner. It could be, it could not be. So that's perhaps also a little disappointing. And then perhaps if you're talking to a very informed general public, they might say, well, I've heard about early universe cosmology, where there is this thing called cosmological inflation that might probe very high energy scales. And then you need to disappoint them again, because currently we don't have evidence for inflation to have happened at a very high energy scale. So perhaps sort of all these three different ways how you might think that you can directly probe quantum gravity effects, they don't seem to be occurring currently in our universe. Of course, I should be fair. There's also no violations that have been observed from some of the principles of quantum gravity that we think should be true. Let's say causality, for example, that is something that we think should be true. We haven't seen any violations of that. Okay, so where does that leave us? Well, this comes indeed back to the Planck scale. Perhaps this just means that really all effects of quantum gravity are tied to the Planck scale. And this could be true. So when you think about the Planck scale, here I write down the Planck length, that is 10 to the minus 35 meters. And that's just an extremely small length scale. So it could just be the case that because this length scale is so small, it's just extremely difficult to directly probe quantum gravity effects. And that's a very reasonable point of view to take. But if this is the case, then you might be a little skeptical that it would be possible at all to someday in the far future to directly access quantum gravity effects. So what I hope that I will convince you of today, there are certain aspects of quantum gravity that do have implications at large distance scales or low energy scales. And sort of the overarching goal of the type of research that I do is to try to understand what are these aspects that do have implications at low energies. So what is the evidence that I have for that? Well, there's sort of three main examples or principles that I think seem to point into this direction. And one of them is the holographic principle. So when I take a subregion of space-time and I try to associate an entropy to that system, then if you're used to sort of ordinary quantum systems, those typically satisfy a volume law. So the entropy grows with the volume of the system. It turns out that in gravity or quantum gravity, this is not true. And instead, we think that the entropy scales as the area of the subsystem. So you might say that this is something that you can think of as sort of a low energy / long distance implication of quantum gravity. Because this area can be very large, we need to have some reduction of degrees of freedom compared to Q of t in order to find something consistent with this area law. So of course, it doesn't mean that this is directly observable, but it does mean that this is at least one aspect of quantum gravity where you might expect that there are implications at long distance scales. Another example is the black hole information paradox. When we think about black holes that are evaporating, then we know from the black hole information paradox that we need to have an order 1 modification to the semi-classical description of Hawking radiation at regimes where the curvature is still small, so when the black hole is still very large. So you can describe this as sort of a breakdown of the semi-classical approximation at a regime where you typically don't expect it because you still have small curvatures. And sort of understanding this presumably will teach us something important about quantum gravity. And the final piece of evidence go by the name of swampland constraints. Maybe not everybody is familiar with that term. So who's familiar with the term swampland constraints? Okay, but I would say slightly less than half. So for those of you who are not familiar with swampland constraints, the idea of the swampland program is the statement that if I take some effective field theory that is not coupled to gravity, that might be a completely fine effective field theory, but at the moment that I couple it to quantum gravity, there can be certain pathologies that arise. So what that means is there are certain constraints that effective field theories need to satisfy if you want to consistently couple them to quantum gravity. So you can roughly think about the set of all these constraints as some low energy implications of quantum gravity. All right. So all these sort of different aspects that I hinted upon, they're all very closely related to black hole physics. So if you want to understand these aspects, then it seems very natural to study black holes. So for example, when you think about a black hole, it has an entropy that scales with the area of the event horizon. So we have this sort of reduction of degrees of freedom that seems to be going on in black holes. Of course, Hawking showed us that black holes emit Hawking radiation, so they evaporate, so they give rise to this black hole information paradox. One of these swampland conjectures that is very closely tied to black hole physics is the weak gravity conjecture. So I'll not talk too much about that today, but that's another piece of my research that I work on. And in particular, what we will focus on today is mostly quantum corrections in black holes that are close to extremality that are larger than you might initially expect. And in particular, what I will do, I will explain sort of the nature of these quantum corrections. I will study them in the context of charged black holes in de Sitter space, which sort of kills two birds with one stone because it allows me to both study black hole spacetimes as well as cosmological spacetimes. So that sort of is the motivation for the type of work that I want to present to you today. So the rest of the talk will be as follows. I will explain more in detail what the quantum corrections are that I'm interested in and how they were found in the context of near-extremal black holes. Then it turns out in order to sort of describe them well and understand them well, it's very useful to have a nice thermodynamic description of these black hole solutions. And that led us to understand the thermodynamics of black holes in de Sitter space. But already there were some open questions that weren't fully addressed that we needed to work on first before studying the quantum corrections. And so that will be the main part of what I will be presenting today, sort of trying to understand the thermodynamics of these black holes. Then we'll see some applications of these new first laws to describing these type of quantum corrections. And then I will summarize and hint on some future interesting directions. But before we do that, maybe I should pause and ask if there are any questions. All right, very well. So that brings me to quantum corrections in near-extremal black holes. So maybe let me not assume that everybody knows what an extremal black hole is. I've already mentioned that word a few times. Let me give you just sort of a brief introduction into what an extremal black hole is. When we think about black holes that just have a mass, they are described by the Schwarzschild solution, and we know that those have a horizon which is proportional to the mass of the black hole. Larger the mass of the black hole, the larger the black hole itself. And as Hawking showed us, the temperature of those black holes is inversely proportional to the radius of the event horizon. Larger black holes have a smaller temperature. Okay, so this is just what happens when we think about a black hole that just carries mass. Let's say that we add another conserved quantity to the game. For example, we take a Schwarzschild black hole and we throw in a bunch of electrons. And then we obtain not a Schwarzschild solution, but a so-called Rice-Nordström solution. So this is a black hole that, in addition to its mass, also has a charge parameter. And what happens to this solution is something interesting. Instead of just having one horizon, now these charged black hole solutions, they have two horizons, which you can indicate by R plus minus. So it means R plus is the outer horizon of the black hole and R minus is the inner horizon of the black hole. If you take that metric and you compute the Hawking temperature of those solutions, you find that it scales as follows, as the difference between the two horizon radii. In particular, if you now impose that that temperature is positive, you get a bound on the amount of charge that you can add to these solutions. So if you have a solution that satisfies this constraint, it's a regular black hole solution. If you would take a charge that is too large that violates this bound, you would end up with a naked singularity. So precisely when this inequality is saturated, what happens is that the temperature goes to zero, and these zero temperature solutions are what are known as extremal black holes. And they are interesting for a variety of reasons. In particular, one thing that people noticed already quite long ago is that there are two puzzles when we start to think about black holes that are close to extremality. So the first of them is the following. When you take a thermodynamic approach and describe what is happening to the system near extremality, you can compute what happens at zero temperature, then the area of the black hole still remains finite. In particular, if we take the Bekenstein-Hawking formula for the entropy that scales with the area, it also means that the entropy in that limit is still finite and large for a macroscopically sized black hole. And in particular, this now means that you have a very large density of states sort of in the ground state of the system at zero temperature. So this seems at odds with the third law of thermodynamics, which at least roughly speaking tells us that if I take a zero temperature limit of a solution, the ground state shouldn't be very largely degenerate unless there's some symmetry principle that causes that to be the case. So for general extremal black holes, there doesn't seem to be at least any obvious symmetry principle that would tell you that there's such a large degeneracy of ground states. So this seems a little bit puzzling. It's maybe not incorrect, or it's maybe not a pathology, but it seems puzzling. So then the name of the game is to either uncover this symmetry principle or show that there are corrections that lift the ground state degeneracy. And we'll see precisely what will happen. The second puzzle appeared in this paper by Prescott et al. In 1991, and that tries to understand in what regime is the semi-classical thermodynamic description of extremal black holes or near-extremal black holes valid. Because typically when we describe Hawking radiation, we always assume that the Hawking modes that are being evaporated typically only have a small back reaction effect on the geometry. So for instance, if I emit a Hawking mode, then I typically assume that the mass and the temperature of the black hole doesn't change by a whole large amount. So this is valid for charged black holes when they're sufficiently far away from extremality. But when you get close to extremality, this approximation is no longer valid. And one way of seeing that is when we think about the typical energy above extremality of near-extremal black holes. So that is indicated by the orange curve. That is something, that's an energy that scales quadratically with the temperature.
That's energy of radiated particle.
Sorry?
That's the typical energy of what? Of radiated particle?
So the orange line we can think of as the sort of the available energy above the ground state of the black hole. And this second line, this blue line, is precisely the typical energy of the radiated particle indeed. So when you just look at the mass above extremality, that is this quantity E-extremal. When you expand it for small temperatures, it scales quadratically, but the energy of a typical Hawking mode indeed scales linearly with the temperature. So now you see what happens is that when we're far to the right of this curve, the energy of a typical Hawking mode is small with respect to the orange line, and we should be able to use our standard semi-classical thermodynamic description. But if it goes close enough to extremality, to small enough temperatures, at some point these lines will cross. And this is a regime where you do expect that the semi-classical description breaks down. So the question is, are there any quantum corrections that we expect there?
But is this going to happen then for any black hole that's evaporating, eventually going to cross lines?
Yeah, good question. So typically, when we think about, for example, just Schwarzschild black holes, then this doesn't happen until you are at the point where the black hole itself is very small.
Yeah.
So then it becomes highly curved, and we anyhow don't expect GR to work anymore. But this situation is a little different because this is still a black hole that is of macroscopic size. At 0 temperature, it's still macroscopically large, but there are these corrections that we expect.
I see. Yeah, because people use this effect for the usual case for the primordial black holes.
Yeah,
they claim that could then be dark matter. And
that's right. Indeed, so that's a slightly different regime. So there we're more in the situation where we say those black holes have Planckian curvature, so we definitely expect quantum gravity to be important. This is a slightly more subtle situation where it seems that quantum effects already show up at a scale that is still a distance scale that's much larger, which is why this I would say is wouldn't say it's more interesting, but it's a different regime. Yeah, good question.
So so temperature is inversely proportional to the mass.
Yeah.
So after which,
But you need to be a bit careful here because there's charge also. But yeah.
I was just wondering, like, which scale of mass of black hole should I take to keep this great temperature?
Oh, I see. Yeah, so I think it's one thing that you can do. So this is the temperature here is expressed in terms of the Planck length and the charge. So it depends on the amount of charge or mass that you have on it.
Because this is why probably you have a much larger scale, right? Because you have another parameter here, which is the Q.
That's right, exactly. Yeah, that's right. That's why you can play this game.
I see.
Yeah. All right, so this was the fact that this happened was sort of known for a long time, but I don't think it was completely clear, like if there are quantum corrections that appear here, what are those? And it's only relatively recently that this has been resolved. But before I explain that to you, let me sort of give you a thermodynamic diagnostic that tells you that these quantum corrections should be there. And the way you can derive that is roughly as follows, and this is what they did in the Preschool et al. Paper. So the location where these two lines cross, where you expect corrections to become important, is when delta E is proportional to delta T. So if you now use the first law of thermodynamics for these black hole solutions, you have a variation in the mass, temperature, a variation in the entropy, then this phi of B is the electric potential and a variation in the charge. If you now use the first law at fixed charge, so you work in an ensemble where you fix the charge, and you now compute the specific heat, so TB delta SB divided by delta TB, you use the first law at fixed charge, you precisely land on this equation, which then if you plug in that delta E is delta T, thinking of delta E as delta M, then you find that this crossover point precisely happens when the specific heat becomes 1. So whenever you find a heat capacity that is of order 1 or smaller, that is where you expect the sort of semi-classical thermodynamic description to break down. And sort of the somewhat intuitive reason why this is that diagnostic is that if you have a specific heat that goes to 0, what it means is there are no longer a large amount of degrees of freedom available to either absorb or emit heat. So that is why your thermodynamic description might break down. All right, so as I mentioned, these sort of two puzzles have recently been addressed. It started with this work by Toriachi and Iliescu in 2020. Since then, there's been quite a lot of follow-up work studying this effect for different types of black holes. And sort of the approach that they took is the following. So they were interested in basically studying the thermodynamics of these solutions by making use of the Euclidean gravitational path integral. So typically what you do is if you have a Euclidean gravitational path integral, that is given by the following expression. So here I allow for integrating over different metrics, G, also potentially different matter couplings, phi. Yeah.
So this is how many space-time dimensions?
So this in principle is general. So they did this for different types of black holes.
How do you think it's possible?
Good question. So what you typically do is you use a saddle point approximation. I think the original paper did it for 4-dimensional Rice-Nernst black holes. Since then, it has been computed for many other types of solutions. In particular, one that you might like is for the BTZ, because there we know the exact partition function from other sort of ADS-CFT reasoning. So typically what you do indeed in order to find this, compute this partition function is you use a saddle point approximation, where there's a leading saddle that hopefully corresponds to the black hole solution that you like. And then that is typically equal to minus the classical entropy of that solution. But then on top of that, you can have quantum corrections that are associated to fluctuations of these different fields. And in principle, this is an infinite tower. Typically, you have to assume or show that these corrections are small in order to correctly truncate this expansion. But one of the nice things about these works, so this is what I mentioned, one of the nice things about these work is that what they did is, because they were looking at near-extremal black holes, near horizon geometry of those solutions is ADS2 times S2. It is a nice Jackie-Teitelbaum gravity description that allowed them to compute these corrections and also show that they are one loop exact. So it gives you sort of the full answer. So what they found there was sort of surprising when they did this computation. They found that this one loop partition function scales as the temperature of the black hole times some power alpha, where this power alpha sort of depends on the precise black hole solution that you're looking at. In particular, what you see happening now is when you take t to be small, then it's no longer guaranteed that this second term is smaller than the leading contribution. So what happens is when you get sufficiently close to extremality, the quantum corrections start dominating over the classical saddle. So that means that, as we suggested, that the semi-classical description really breaks down there. But the power of JT gravity allowed them to still show what happened in that regime. Okay, so what are the consequences of this computation? In particular, for sufficiently small temperatures, this leads to a large deviation of semi-classical thermodynamics, because these quantum fluctuations, they start to become very important. So in some sense, this addresses the second puzzle. So there's this specific heat that goes to zero, which suggests that there should be quantum corrections that we need to take into account. And indeed, by doing this one loop computation, we saw that those quantum fluctuations are indeed there. Now, if you use this result for the partition function and translate that to a density of states, you find a large deviation from the semi-classical result that is indicated in the following graph here. So if we just use Hawking's computation and still say the Bekenstein-Hawking formula should hold at extremality, what it would predict is that there's a density of states at zero temperature that scales exponentially with the area of the black hole. And this is this large ground state degeneracy that I mentioned. But then taking into account these corrections, you actually find that this density of states is modified and seems to go to zero all the way when you take the zero temperature limit. So what that means is when you're in this regime where there's this large deviation, the semi-classical extremal or near-extremal black hole that we had is no longer the correct description of the system. It's really some highly quantum system that is fluctuating and it presumably doesn't have a nice metric description. Okay, so that is quite dramatic. It really shows us that extremal black holes behave quite differently than what we initially thought. Okay, so that brings me to sort of where we got interested in this problem. So the original papers, they show this behavior for near-extremal black holes, mostly in flat space, but then also the BTC black hole later. So you might wonder, are there other possible geometries where we can sort of try to extract similar quantum corrections? And there have been some recent works that suggested that perhaps similar corrections might also be important for cosmological spacetimes or also black holes in cosmological spacetimes. So we were specifically interested in trying to understand this effect for black holes in de Sitter space, also for other reasons. And we were interested to first understand the thermodynamics of these black holes, such that we could compute the heat capacity which is one indication where we might expect these corrections to show up. So we delved into the subject, but then we quickly realized this actually required a refinement of the existing first laws of thermodynamics for these black hole solutions. So that is the first part of the work that we did, that we now finished. But I've now also presented sort of the more general motivation of why we're interested in this problem. All right, any questions before we talk about that? Yeah.
I have a question about the slide 13. Yeah, how does the density of states go at large?
So at large, I think this picture, I'm not precise. So I took this figure from this reference. I think this becomes closer and closer to the semi-classical prediction. So it will follow the dashed line.
Okay, fine.
Yeah, I'm not sure like precisely about the curve. I guess you would at all times, or sorry, you would, at large energy, I think you would just expect it to scale with the area. And then you have to show like how the area scales with the mass, which, okay. So it would scale, we have to plug in the location of the horizon, which is like m plus squared m squared minus q squared. So that way you should be able to reproduce this plot.
Why did you pick P-sitter instead of ADS, or is there a particular reason?
Yeah, we had a secret motivation that we will not talk about too much today. Mostly I'm interested in the sitter because it sort of, it describes our universe. So any type of quantum correction that you might understand there seems interesting. In a previous project, we were already interested in studying the decay of these type of black holes. So we used that some of the things that we sort of used in that paper seem to be relevant for describing the thermodynamics of these black holes. So that was sort of, I guess there was a more philosophical reason as well as a practical reason.
When you say the computation of quantum correction to the classical action,
yeah,
does that mean you take a sum of the functional determinants of the graviton and all other matter fields?
Yeah, indeed. So that's right. So typically to do these computations, you look at all possible matter fluctuations. So the way how the original paper did the paper from this near-extremal JT gravity perspective, then I think there's only one fluctuating degree of freedom that you have, which is this dilaton field. But since then, people have done the 4D computation, and then indeed you look at sort of graviton fluctuations and also gauge field fluctuations. Yeah. For the Rice-Nordstrom, or for the BTZ case, so there's a three-dimensional ADS black hole, then you just have a graviton, there's no additional matter, which just makes the computation a little simpler. Also, the partition function for BTZ is known exactly, so you don't need to do any work. All right. Okay, so let me now switch gears a little bit and sort of more generally talk about black holes in de Sitter, their thermodynamics, and we'll see then how this relates to the heat capacity and the quantum fluctuations. So when we take charged black holes in the de Sitter space, instead of two parameters, the mass and charge, there's now a third parameter, which you can take to be the de Sitter length, which sort of describes the size of the de Sitter universe that you're looking at. So in this geometry, because you have three parameters, now there are also three horizons. So just like a Rice-Nordstrom black hole, there's an inner black hole horizon and an outer black hole horizon. And now in addition, you also have a cosmological horizon RC. So in general, if you look at the metric for charged black holes in de Sitter, it looks pretty innocent, but surprisingly, the precise expression for the horizon radii in terms of mass and charge and de Sitter length is quite complex. So you always need to be a bit careful in order when you actually do computations. And we in particular will also focus on four-dimensional solutions. So one of the intriguing aspects of charged black holes in de Sitter space is when you look at the phase space of regular solutions, it forms this compact shark fin region. So meaning here I plot the charge and the mass of different black hole solutions, and everything that is within this shark fin region that is shaded corresponds to a regular black hole solution with some particular value of charge and mass. Everything that is outside of this shark fin region corresponds to something that will be a naked singularity. So now there's sort of a richer notion of extremality for these type of black holes, because the shark fin is bounded by these two lines. So in particular, if we look at this upper line here, this is sometimes called the cold branch, or described as cold black holes. So these are black holes for which the inner horizon and the outer black hole horizon coincide. So in a very similar way as the Rice-Nordstrom solutions. But there's still a finite distance between the black hole horizon and the cosmological horizon. And the near horizon geometry of these solutions is ADS2 times S2. Then this lower line is known as the Nariai branch. These correspond to solutions where the outer black hole horizon coincides with the cosmological horizon. So these are the largest black holes that you can fit inside of a cosmological horizon. And interestingly enough, the near horizon geometry of those solutions is DS2 times S2. And finally, you can take these two lines together. They merge into a single point, which goes under the name of the ultra-cold point, which is a near horizon geometry of Minkowski space times S2. So if you're a fan of maximally symmetric spacetimes, this is a really nice solution to look at. In addition, there's one other special class of solutions that will be important for what I will be doing. Those are known by the lukewarm line or lukewarm black holes. So here, those follow this dashed curve, and just for, I guess, illustrative purposes, this line I just exited here, but these are not regular black hole solutions, but if you cut it off here, it's just a bit hard to see the line. These are called lukewarm black hole solutions, and they have a temperature that is equal to the temperature of the cosmological horizon. So in general, the two temperatures of both the black hole and the cosmological horizon is different, but there is this special line where they coincide. So you can think of those as thermal equilibrium solutions, and sometimes it's useful. All right. So when you want to, yeah, sure.
So, take a large black hole.
Yeah.
Its heat capacity is negative.
Yeah, so for, let's say, Schwarzschild black hole, yeah, that's right.
Yeah, so how can we equilibrium?
Yeah, that's a good question. So yeah, I guess the question is basically what does the specific heat like? What does the heat capacity look like when you are at this branch?
That's my question.
That's your question. It depends where precisely you are, but in general, it's positive. So this, yeah. So the sort of the resolution. So what happens is that dynamically these black holes will decay, but you don't not just need to look at Hawking radiation, but also take into account the possible emission of charged particles. So there's some interplay between Hawking radiation and Swinger power production. But indeed, in general, the heat capacity can behave quite differently in different parts of this diagram, and we'll see some examples of that. So in general, if you want to define a first law of thermodynamics for these type of black holes, there are sort of several complications that arise. One of them is that you don't have a nice global timelike killing factor. So in flat space or outside of a black hole, there's always a timelike killing factor that you can use to define a surface gravity, for example. In the Sitter space, there are only finite regions where a killing factor is timelike. So that is one complication that you need to deal with. The other one we already alluded to is because there are multiple horizons, there are typically, the system is typically not in thermal equilibrium, and you have different temperatures and heat flow. Yeah.
So in ADS, you have full timelike curves.
Yeah.
Avoid that by going to universal cover. So if you do something like that here, can you actually make killing vector, which will be globally defined?
Oh, I see. I have no idea, actually. That's a good point. It would be interesting to understand. I never thought about it that way. Yeah, that's a good question. If you really need sort of to have this timelike killing factor to define the thermodynamics.
Yeah. Maybe like something like this similar kind of.
Yeah, that could be true. That's a good point. I haven't really thought about that. Might be interesting. Indeed, but indeed, so in general, you need to think about sort of having these different temperatures and sort of how do I describe the thermodynamics of a system that is not in thermal equilibrium. So let me just take a sort of a higher level point of view. What do we do typically when we define the temperature of, let's say, a black hole solution? So let's say for convenience, we're working with a spherically symmetric metric. Then typically what we do in order to define the temperature of an horizon, which I indicate here by R0, is we use a timelike killing factor xi that is proportional to this flow of this time direction. And this scaling factor describes the forward velocity of some trajectory at a constant radius. And there's always the option of having a normalization constant gamma there that still solves the killing equation. So there's always the freedom to do this. And normally you don't really worry too much about this normalization, but we'll see for the black holes that I'll be looking at, this turns out to be quite crucial. So then from this forward velocity, you can define a local acceleration defined as follows. So you open Walt's book and you look at how he defines local acceleration. Then what you find is when you look at the acceleration associated with this killing factor, because it's defined with respect to divided by the norm of the killing factor, this becomes independent of gamma, but also it diverges at the horizon. And physically that makes sense. If you are an observer that sort of wants to hover precisely at the horizon of a black hole, you need to have infinite acceleration in order to stay at constant radius. So then the surface gravity is defined from this acceleration by taking the limit of this acceleration where you go towards the horizon, but then you multiply again by the norm of the killing factor in order to remove this divergence. So what then happens is that now you have a surface gravity that does depend on gamma, but it's finite at the horizon. And typically the interpretation that you can give to adding this norm of the killing factor is that in this spherically symmetric metric, this becomes equal to minus f evaluated at r0. So you can think of it as a redshift factor. So what this does is this expresses the surface gravity as a local acceleration at an horizon, but then redshifted to a different observer. So in general, when you just think about gravitational redshift, let's say of photons, then we know in a spherically symmetric metric, what happens is that the ratio of these wavelengths behave as follows. So it's a ratio of the different functions f of r evaluated at these different locations. So for example, I can compare the wavelength of a photon at the event horizon and some region very far away. So as I mentioned, what it means is that the surface gravity is an acceleration of the horizon expressed in the frame of an observer at RO. And the location of this observer is given by this choice of gamma squared. So if I'm choosing a different gamma, what it means is I'm expressing the acceleration with respect to a frame of a different type of observer. So in some sense, you can think of that when I pick a normalization for my killing factor, what I do is I pick an observer with which I want to express the temperature. Okay, so this was maybe a little abstract. So let's just give two very simple examples where you typically don't really think about the normalization because it's trivial. Let's say that I take here a Schwarzschild black hole solution. And then you might not realize it, but when you compute the temperature, you are comparing to what an observer at infinity sees. So then I take RO to be infinity. My location of my R0 is at the event horizon of the black hole. And then you see that if I take RO to infinity, if I just look at this function, I see that it becomes equal to 1. So that means if I, for a Schwarzschild solution, if I want to express the temperature with respect to the observer at infinity, I have to pick gamma equals 1, which is what you normally do. You can give a second example that is maybe slightly more interesting. Let's say that I look at empty de Sitter space, so just pure de Sitter space, which has a function f of r that looks like this. Then the cosmological horizon is dependent on the observer that you choose. So then it makes sense to just pick an observer that is, for example, located at R0 equals to 0. Then if I choose that observer there, the cosmological horizon is located at R0 equals to L. When I take R0 equals to 0, I look at f of r. It again is equal to 1. So that means that I should again pick gamma equals 1 in order to describe the thermodynamics. Now you might guess what happens now when I think about charged black holes in de Sitter space, or more generally uncharged black holes in de Sitter space. Then if you would again take this normalization of gamma equals 1, then you find that you express the location of the observer RO at either a location that is inside the inner black hole horizon, so R0 smaller than RA, or the other option is that you place it outside of the cosmological horizon. Both options don't seem super physical because typically if you want to describe the temperature of both systems, you want to be in between the two different horizons. So this is, if you pick gamma equals 1, that's not a very natural place to put your observer. And this was the choice that was chosen before in order to derive the thermodynamics of of these types of black holes. So when you do take this psi equals partial t normalization and derive first law, so that was done, for example, there was a nice derivation in this paper, then you get first laws that look as follows. So you have variations of mass, entropy, and charge again. And you have two of them, one of the black hole horizon and one of them associated with the cosmological horizon. So if you just check these relations, they are correct. They don't seem to be the physical relevant first laws. In particular, as I mentioned, these first laws, they express the temperature with respect to an observer that is not just located in between the outer black hole and the cosmological horizon, but it's expressing this in terms of an observer that is behind an horizon and that is also accelerating. So one of the peculiar aspects of choosing this normalization is that when I take this Nariai limit where the black hole horizon and the cosmological horizon becomes equal, then the temperature defined in these first laws goes to 0. That seems very strange when you think of the near-horizon geometry being two-dimensional de Sitter space, because typically we think that two-dimensional de Sitter space has a finite temperature. So this is one hint that this normalization that was chosen previously doesn't seem to be super physical.
Also, I actually thought that the Nariai temperature is 0. It is not.
But the correct answer would be it depends on your normalization. I would say physically, if I look at the DS2 near horizon geometry, then of course it also depends where, when I say that DS2 has a finite temperature, that statement depends on where I pick the observer to be, where does my observer live. What I will argue is that in order to, when we say that DS2 has a finite temperature, we're typically talking to the observer at the center of the static patch. If you choose the normalization that I will suggest, then you'll precisely in the near horizon limit, RO will correspond to that location. So indeed, so I would disagree in saying Nariai black holes have 0 temperature. I would disagree.
But for the empty de Sitter,
Yeah.
could you still define a global timelike killing vector? Is that what, it's still not possible, right?
Yeah, so there's no global timelike killing
Because
factor
once you
there.
go outside the
That's right.
line,
So the typical way how we think about it is that we just want to define everything sort of to the causal diamond of the observer, and then you're just looking at a static patch, and that doesn't have a global timelike killing factor, but it's timelike within the static patch.
So the metric will have some time dependent factor, and if you do the global metric for the full de Sitter solution.
So the metric of empty de Sitter space is not time dependent.
So then how do you see that that you can't define a global timeline?
Oh yeah, so when you cross the horizon,
Yeah.
so when you take R bigger than L, this flips sign.
That's all.
Yeah, so it's similar to like if you just enter an ordinary black hole. Yeah.
But you can't extend it there.
Well, so indeed, so that's a little bit tricky. So strictly speaking, static coordinates only cover the finite static patch. So if you want to do it,
It's not like the standard black hole, which can be extended past the horizon.
so
You see it from the Penrose diagram for de Sitters.
Yeah, what you can do indeed is you can go to global coordinates, which cover the global de Sitter space. And then in each, let me draw the diagram. So what you can do is in each of the 4 quarters of the diagram, you can.
Take a blue marker.
I can put that one in the garbage.
Yeah.
Let's see.
Yes.
So this is the Penrose diagram of de Sitter. So indeed, static coordinates typically only cover one of these quarters. What you can do is you can choose 4 different coordinate systems in each of these quarters, and then use
Yeah, it's different coordinates.
different coordinate system indeed. So in order to see that the killing factor flips sign, I mean, killing factors are coordinate independent. So you can use a different coordinate system that covers them all to make this statement. All right. All right, so as I already alluded to, so I would say the resolution to get a more physical description of the thermodynamics of these solutions is to adapt the normalization to a more natural observer. So in particular, if you focus on the region that is outside the black hole horizon, but inside the cosmological horizon, it turns out that there's a unique observer at fixed radius that is non-accelerating, that precisely hovers between the 2 horizons. So the gravitational attraction cancels the cosmological repulsion. So that seems a very natural observer to try to adapt your thermodynamics to. And we were not the first ones to describe this. This actually already appeared in a pretty old paper by Bousso and Hawking in 1996, where they did it for the uncharged black hole solutions. But surprisingly, nobody really wrote down the sort of the new first laws associated with this other normalization. And maybe one reason is that if you try to solve for the location where this observer lives, then the first side, oh, it just looks like a quartic polynomial. That's okay, right? But if you have some familiarity with quartic polynomials, you know that the general solution looks very complicated. I should say in the case that Boson-Hawking studied, this is not so complicated. It's only when you introduce also the charge that it becomes such a mess. But there is a way to think about the different extremal limits to still make sense of these this expression. So when you take this more physical normalization, we come back to the earlier question. We can now compute what is the behavior of the temperature in different extremal limits of this diagram. So for example, if we again look at the cold branch, so now I indicate tilde to mean sort of the normalization that I like, then you still find that those black hole solutions have zero temperature, just as the ultra-cold black holes have a zero temperature. But now the Nariai branch in general doesn't have a zero temperature, and you find that the temperature is precisely equal to 1 over 2 pi L2, where L2 is the two-dimensional de Sitter radius. When you take the limit where you go towards the ultra-cold point, this L2 diverges, and that's why you get a zero temperature. Okay, so now armed with this knowledge, we can now rederive the first laws. Was a question? No, okay. So just sort of technically, in order to do this, because we have these two different temperatures in general of the black hole and the cosmological horizon, it's sometimes useful to introduce what is known as a York boundary. So a York boundary is sort of an artificial boundary that you introduce in your system in order to carefully define your thermodynamic ensemble. And at the end of the day, you might take it to zero. And that is precisely what we did in order to derive these first laws. We introduced a York boundary at this location Rho, and doing so, there's a standard procedure for deriving the first laws. So this isn't the original reference, but it's a more recent one that we found quite convenient. So when you do that, you find the following expressions for the first law expressed in terms of this normalization that is more physical. So this quantity delta E is what is known as the Brown-York energy. And then in addition to the terms that you might have seen earlier, there now also is a pressure term at Rho and a variation of the area of the York boundary. But as I mentioned, we sort of introduced this York boundary very artificially. It was just a useful tool in order to derive these first laws. But now we actually want to remove its dependence. And importantly, what we are doing is a little bit different from the standard way how you normally think about York boundaries. So normally, if you think about the York boundary, you fix a location at a fixed radial coordinate, and you treat it as sort of varying that boundary, you treat it as an independent variation. But in our case, the location Rho was determined by solving this equation. So that means in particular that the variation of Rho is not independent from the mass and charge variations. So now what you can do, you just define a delta m tilde in the following way. So you recognize this as the old definition of mass, but now redshifted with this vector. When you define this mass variation, the previous first laws that we had take this form that looks very similar to the old expressions that we had, except there are now tildes that appear here. But that will be an important difference. And you can think of these new first laws as just taking the old first laws and redshifting them to a frame that is more natural. So that sounds pretty simple, and you might wonder, okay, does it have any interesting implications, or what are its applications? So you might wonder, like, when does this matter? Well, it turns out for some thermodynamic questions, this really doesn't matter, and the normalization drops out. So for example, you can look at the two different first laws for the black hole and the cosmological horizon, and you can just subtract them. This is a type of first law that people look at, and because then there's zero that appears on the left-hand side, any overall normalization just drops out. So when you, for example, study this thermodynamic identity, there the normalization that you choose really doesn't matter. However, because R of O depends on mass and charge, normalization will be important when we start taking derivatives. And in particular, when we start to look at the heat capacity, then this will become important. Now we go all the way back to the beginning of the talk. I was talking about quantum corrections related to the heat capacity. That was the reason why we're interested in studying this heat capacity. And it's clear that in general, because R of O depends on mass and charge, that the heat capacity expressed in the sort of old normalization will generally not be equal to the heat capacity expressed in this more physical normalization. So let us precisely look at the difference. So I showed you this expression for R of O in general, which looks horrible. So it makes most sense to either just plot this numerically or look at particular limits. I will choose the second option. So here in the first column, I plot the old heat capacity, or I display the old heat capacity for different types of interesting solutions. And you find, so this was known before, that those are all zero. So based on a previous reasoning, you might say, oh, quantum correction should be important for all these different black hole solutions. So I highlighted the Nariai solution, the cold solution, ultra cold, and also this intersection of the Nariai line with the lukewarm line. And in particular, you see two differences. So for the Nariai black hole, we already saw that there was a difference in the temperature. Now you see that the general expression for the heat capacity is finite. There's also this other behavior where you see that the intersection of the Nariai and the lukewarm line, there's a divergence. So whether it's positive or negative depends on how you approach that point. But what this means, so we'll come back to this divergence in a moment. What this means, that the fact that you get, in general, a finite heat capacity for the Nariai solution is that in general, you don't expect to have large corrections for these type of solutions. So now let's take a little bit of a closer look how the heat capacity behaves along the entire Nariai branch. So here I plot the heat capacity as a function of the radius of the black hole. So all the way to the left, these correspond to uncharged Nariai solutions. So these are Schwarzschild de Sitter solutions where I take the black hole horizon as large as possible. You find in general that the heat capacity is negative. These are unstable solutions, but it's still large. So you don't expect to have large quantum corrections in this limit. Then you start increasing the charge, and at some point you hit this intersection of the Nariai and the lukewarm line, where there's a divergence. If you approach it from the left, it's minus infinity. If you approach it from the right, it's plus infinity. Sometimes diverging heat capacities are associated with phase transitions. We think something similar is happening here, and we would like to understand that a bit better. If you go all the way to the ultra-cold limit, you do find that the heat capacity goes to zero. So this is a regime where you do expect quantum corrections to become large. So that leaves us sort of with two questions that we still need to answer. Because up to now, what we did is to compute the heat capacity, we worked at an ensemble of fixed charge. And this leads in particular to two problems. So one problem we already noticed, which is that we got this diverging heat capacity at the intersection of the lukewarm and the Nariai black hole. And the second one you didn't realize yet because I didn't show it to you, is that when you look at variations at the ultra-cold point, if I fix the charge, that means that variations will be guaranteed to exit the shark fin. So again, this doesn't seem super physical because, as I said, all the regular black hole solutions should live inside of the shark fin region. So if I want to understand the heat capacity at the ultra-cold point, what I need to do is to work at a different ensemble that corresponds to variations moving in this direction. And the way to do that is to not work at an ensemble of fixed charge, but to fix the charge to mass ratio. And actually, both type of problems sort of can be resolved by working in this different ensemble. In particular, when I fix the charge to mass ratio to be z, then my first law takes the following form. So I choose to express it in terms of a mass variation. So it just turns out to look at the divergence that appears in the heat capacity at the intersection of lukewarm and Nariai. And one way to counter it is to take a unique charge to mass ratio for which the heat flow actually vanishes. So you can sort of think of it, there's an infinity, you try to cancel it by having something that is zero. But interestingly, what it means is there's a unique heat capacity for which the unique charge to mass ratio for which the heat capacity remains finite. And in particular, it corresponds to this precise value. We think there should be a nice, more microscopic interpretation why this precise charge to mass ratio appears. But at the moment, this is just an interesting observation that we would say don't fully understand. Coming back to the ultra-cold point, again, if we look at trajectories that remain within the shark fin, so those correspond to this purple dashed line, again, there is a unique charge to mass ratio that describes variations that remain within the shark fin. And again, this corresponds to a location where the heat flow vanishes. Now, because the electric potential looks a bit different at that point, the precise charge to mass ratio looks a bit different. But if you compute the heat capacity of the ultra-cold black hole in this ensemble, you still find that it vanishes. So that gives us confidence that there should be large quantum corrections in this regime, sort of regardless of the ensemble that you take. All right, so that brings me sort of closer to the end. So we sort of have these results of the heat capacity that gives us, you can think of as a prediction of where quantum corrections should become large in a similar way that they did for the rising Nord-Star black hole. And in particular, we would like to understand also microscopically this behavior of the heat capacity. What does it tell us about sort of the, I guess, microscopic condensed matter system that is describing these black hole solutions? And we think that there's something interesting to be learned there. As I already alluded to, divergences in the heat capacity can be typically associated to phase transitions. So you might wonder if something similar happens here. I think physically it makes sense because what happens when you cross the lukewarm line is that you switch the role of which temperature is larger. So below the lukewarm line, the black hole temperature is higher than the cosmological temperature, and above the lukewarm line it switches. So you might wonder, does this phase transition tell you something about these microscopic degrees of freedom that make up the black hole? And we now, perhaps most importantly, we now have a prediction where we can try to do similar one-loop computations in order to find where quantum corrections are important. So that brings me to the summary. So what we did is we derived new first laws of thermodynamics for four-dimensional charged de Sitter black holes, adapted to, I would say, a physical observer. Using those, we computed the heat capacity of different extremal solutions. And what we found is that the heat capacity vanishes for cold black holes and ultra-cold Nariai black holes. So this gives predictions where quantum corrections should become large in a way that is very similar to the rising Nordstrom solution. So the next step, of course, and which was our original motivation, is to try to relate our results to these recent computations of one-loop determinants for de Sitter black holes. And it turns out that this is quite subtle. So there are various issues that arise. There's sort of a confusion between, I shouldn't say confusion, there's a subtlety between working in Lorentzian versus Euclidean signature. We worked in Lorentzian signature, these one-loop computations do Euclidean signature. It's not always super trivial to do the Wick rotation, and there are various subtleties that appear. Another question that people have recently started to address is the phase of the partition function when you compute it. If you just naively compute the partition function, let's say an empty de Sitter space, you get a factor of I. It seems a little bit weird, and there are different takes on how to resolve this issue. But we hope that sort of our sort of physical picture can be a little bit of guidance in order to try to resolve this issue. And then finally, it might be interesting to really compare to an existing microscopic model of the de Sitter space, which goes under the name of the double-scaled SRK model, which is proposed to be dual to a three-dimensional de Sitter space. So this is one potential, very concrete avenue where you can try to study these one-loop corrections. And with that, let me thank you.
In one of the slides, like in the beginning part of your talk, you mentioned the one-loop correction goes like log of t to the alpha.
Yeah.
So is this result like very generic for like any black holes or?
Yeah, so indeed, so why I wrote it indeed in this sort of general sense is that whenever these one-loop corrections have been computed for black holes close to accessibility, they always take the same form. And I think there's some, if you look at these Toriachi and Iliesio papers, they argue that this is related to sort of the near-horizon symmetry that is in the game. In particular, this size parameter alpha is related to zero modes that appear in this Euclidean path integral. So what happens is in this path integral, there are sort of the mass of these fluctuations, they scale, I think, linear with the temperature. So you see that they become zero modes exactly at zero temperature and spoil sort of the saddle point approximation. So this alpha is precisely related to how many zero modes you have. So for example, if you take the BTC black hole, there's some counting that I don't remember, but for the BTC black hole, it's like 3/2. So I think there are sort of 3 different types of zero modes that add up that you need to divide by 2 for some reason. If you do this for, I think for the cold black hole in the de Sitter space, I think this is like 7/2. So there are different powers that appear.
And these temperature, like in the second part of your talk, you mentioned there can be like T and T.
Tilde, yeah.
So which T is?
Yeah, a good question. So So far, it depends a bit which paper you look at, but in particular, there's one paper that claims to do the one loop corrections indeed of de Sitter black holes, and they use the T without a tilde. And they do find that there are one loop corrections in the Nariai limit far away from the ultra-cold point. So we would say that those results are a little suspect because they don't use the sort of the physical temperature. There are different results that don't directly seem to rely on sort of the normalization of the killing factor. And this is precisely sort of the question we're trying to figure out, because there are sort of different results in the literature. They are conflicting. Some references say there are one loop corrections for the Nariai black hole. Some of them say they're not. We think that that is related to just this sort of different choice of normalization.
But so are you planning to compute the one loop corrections now you know where to look, or they've already been computed?
So there already have been computations of one loop determinants that have been done. We think that those computations are done in a regime that's not super physical. So this is related to the fact that if you, I guess it's sort of related to this diagram. So one computation that was done is they Wick-rotated to Euclidean sigma to effectively describe a different patch, not a static patch. So when they were looking at the Euclidean description that described this patch at the top, which is called the Milne patch, they found one loop corrections. But we think that is not the relevant patch if you're sort of a physical observer in the Sitter space. So it seems to depend a bit when you say one loop corrections, like what do you precisely mean? Like which geometry are you looking at?
Are you able to take their calculation, rescale it, and get the new?
That's what we want to do. That's right.
You have to compute the corrections completely starting from scratch.
There are enough subtleties in this in these computations that we think that we need to start from scratch. Because there's also these factors of i's that appear, but that we don't fully trust how they've been treated with. So yeah, that's the main reason why we first did the thermodynamics, because we quickly realized this is pretty subtle. And the thermodynamics gave us a nice physical way of at least making some statement. But the next step is really the one loop corrections.
Factors of high diffusion and stability.
Yeah, and that could be very well. So that's a good question. So we know that black holes in the system, they are unstable. So in general, you do expect instabilities there. But then you might counter that like, oh, we know that if we do, for example, a similar computation for Schwarzschild black holes, they're also unstable and there's no factor of I. There's a proposal by Mulder saying how to think about those factors of I. We don't fully believe that that's correct.
Any question? So we'll send the speaker again. Originally we'll cut out at 5:45 for peak hours. I'll just finish this. Yeah.